So far we have been discussing unidirectional transport in a Cartesian coordinate system, where the coordinates are perpendicular to planes of constant coordinate. Okay. So, we will now consider transport in a curvilinear coordinate system, okay, that is unidirectional transport. In curvilinear coordinates. We will consider unidirectional transport in a curvilinear coordinate system. Often we solve problems where we, for example, want to find out heat transfer in a pipe. Okay. Of radius r, say, okay, in a pipe of radius r, or around a spherical particle, okay, of radius r, okay, around a spherical particle of radius of known radius. We could of course solve this particular problems in a Cartesian coordinate system. So, for example, we could set up a 3-dimensional coordinate system here, x, y and z, and r is the radius of the spherical particle, or we could set up a coordinate system here x, y and z, okay, where r is the radius of the pipe, and then we solve the differential equations that we had derived and then apply boundary conditions. In this particular case, we may need to apply a boundary condition of, for example, constant temperature at the surface of the particle, or 0 velocity at the wall of the pipe, or some other such boundary condition at a surface of at a surface, okay, which is bounding the flow. And in this case, the surface that is the boundary of the flow is a curved surface. Okay. So, for example, in this particular case, this equation for the surface can be written as x square plus y square plus z square is equal to r square, okay, for a sphere in 3 dimensions if my origin is at the center of the sphere. Okay. Similarly, in a cylindrical coordinate system, in this particular coordinate, the equation for the surface would be y square plus z square is equal to r square. Okay. So, that would be the surface of the cylinder. So, you have to apply the boundary conditions on this complicated surface. Okay. And that is not going to be a simple task. If you recall, in a Cartesian coordinate system, we had to satisfy the boundary conditions only on plane surfaces at fixed values of the coordinate z, okay, at fixed values of the coordinate z, which was perpendicular to the surface. In this case, the surfaces are curved and they contain dependence on all 3 coordinates, okay, and so applying boundary conditions will be difficult. It would be preferable if we could apply the boundary conditions on surfaces of constant coordinate. Okay. That makes it much simpler, okay, as we saw earlier when we looked at a Cartesian coordinate system. Okay. If we have to apply boundary condition on surface of constant coordinate, that means that the boundary of this of the domain in this case should be a surface of constant coordinate. Okay. In the case of a flow in a pipe, for example, the boundary is a surface which is at a constant distance from the axis. It is a distance r from the axis of the pipe. Okay. And therefore, if I want to apply a boundary condition on a boundary of constant coordinate, one coordinate should be the distance from the axis of the pipe. Okay. One of the coordinates should be a distance from the axis of the pipe. Similarly, in a spherical coordinate system, the surface is at a constant distance from the origin. Therefore, if I want to apply boundary condition at a surface of constant coordinate, one of the coordinate has to be the distance from the origin, from the point at the center of the sphere. Okay. So, we have to use that coordinate in order to derive our balance equations. Okay. That coordinate system has to be used to derive our balance equations. For a pipe, what is used is what is called a cylindrical coordinate system. Whereas for around a sphere, it is called a spherical coordinate system. In a cylindrical coordinate system, the distance from the axis is one coordinate. Okay. And for a spherical coordinate system, the distance from the origin, from the center, is one coordinate. So, let us examine, for example, energy transfer in a cylindrical coordinate system in a pipe, for example. Okay. If I have some fluid in a pipe and it is being heated, the wall temperature is higher than the fluid temperature. How do we determine the energy balance equation for the temperature in the pipe? Okay. So, I will take this as a pipe. And I will consider unidirectional transport, where the temperature, for example, is only a function of the distance from the axis of the pipe. Okay. So, in this case, okay, I can define the coordinate r as the distance from the axis and the coordinate z as the distance along the axis. Okay. For now, I will assume that there is no variation in the z direction, all of the variation is in the r direction. Okay. So, how do we derive an energy balance condition, and from that a differential equation for the temperature field in this coordinate system. Okay. So, the balance condition was what we had used earlier in a Cartesian coordinate system. Okay. Change in energy in time delta t is equal to energy in minus energy out plus any source or sink of energy. Okay. I will write this as production. Okay. So, that is the usual energy balance condition that we have used earlier. Okay. Now, in order to use this energy balance condition, I have to define a differential volume for which I can apply it. Okay. That differential volume should be bounded by surfaces of constant coordinate. Okay. That differential volume should be bounded by surfaces of constant coordinate. Okay. So, if I take, for example, a side view, okay, if I take, for example, a side view, what I will see is the surfaces of constant coordinate are cylindrical surfaces, okay, having each surface is at a constant distance from the axis. Okay. Each surface is at a constant distance from the axis. Okay. So, if the total domain has dimension r, okay, if I look from the top, okay, I will have two surfaces which are concentric cylinders. Okay, two surfaces which are concentric cylinders. The inner surface is at a distance r from the axis. The outer cylinder is at a distance r plus delta r, okay, from the axis. And this direction, the height is delta z. Okay. So, I have two cylinders. the annulus between these two cylinders is the differential volume for which I will be writing the balance equation. Okay. The annulus of this between these two cylinders is the differential volume. Okay. So, it is basically the annulus between a cylinder of radius r and a cylinder of radius r plus delta r. Okay. This is bounded by two surfaces, the inner cylinder and the outer cylinder. Okay. So, I have area of inner surface is equal to 2 pi r times delta z. Okay. 2 pi r is the circumference of the inner surface, 2 pi r times delta z is the surface area, okay, area of the inner surface, and the area of outer surface is equal to 2 pi into r plus delta r times delta z. Okay. Into delta z. That is the surface area of the outer surface. Okay. And the volume is equal to 2 pi r delta r delta z. Okay. The perimeter times the thickness times the height. Okay. 2 pi r delta r is the area in between these two cylinders times delta z, which is the height. Okay. So, this is the differential volume, the volume between two cylinders, annular volume which has inner radius r, outer radius r plus delta r and height delta z. And this is what we will be writing the balance equation for. Okay. So, change in energy in time delta t, okay, is the change in energy density into the volume. Okay. I should note before I progress here that in this case the surface areas of the inner and the outer surfaces are not equal. Okay. In this case the surface areas of the inner and the outer surfaces are not equal in general. Okay. That is because the surfaces are curved. So, at a greater distance from the origin you will have a larger surface area. This is in contrast to the Cartesian coordinate system that we had examined earlier, where the surface areas of the two bounding surfaces were the same, okay, and therefore, we could just take the area out. In this case the surface areas are different. Okay. So, the change in energy, okay, the change in energy in a time delta t is going to be equal to rho Cp into T at r t plus delta t minus T at r t. This is the change in the energy density. Rho Cp t is the energy density. The difference between two successive time intervals is rho Cp times T at r t plus delta t minus T at r t, and this has to be multiplied by the volume because this is a change in energy density. To get the change in energy we have to multiply this by the volume, which is 2 pi r delta z. Energy in, okay, energy is coming in at the surface at r, okay, because the coordinate that I have chosen is distance from the origin. Okay. So, the coordinate that I have chosen, okay, in the cylindrical coordinate system is the distance from the origin. Okay. So, therefore, the radial coordinate is in this direction. Okay. It is increasing as distance from the origin increases. Therefore, at the surface, at the inner surface, okay, if I have two surfaces, at the inner surface a flux in the r direction will enter the volume. Okay. At the inner surface a flux in the r direction will enter the volume, At the outer surface, a flux in the r direction will leave the volume. Okay. So, therefore, the energy in is the energy at the inner surface at r. Okay. Energy in a time delta t, okay, is equal to the flux times the area times delta t, okay, is equal to q r at the location r times the area, which is 2 pi r delta z, okay, into delta t. Okay. That is the energy in at the surface at r. Okay. At the outer surface, q r is directed outward from the volume. Okay. So, that is the energy out. Okay. Therefore, energy out has got to be equal to q r at r plus delta r into 2 pi into r plus delta r times delta z times delta t. Okay. Okay, the flux times the area. At the outer surface, the area is 2 pi into r plus delta r times delta z times delta t. That is the energy out, and any source or sink within the volume, the energy source or sink within this volume, I can write this as S source density, source per unit volume times the volume, that is, okay, 2 pi r delta z. SE is an energy per unit volume per unit time. Okay. It is like if you have energy in exothermic reaction, what will be specified is the energy that is generated per unit volume per unit time. Okay. So, the rate of the energy generated within a time delta t within the volume has got to be equal to SE times the volume times delta t. Okay. Okay. So, these are the terms in the balance equation. Okay. Equate the left and the right sides, rho Cp into T at r t plus delta t minus T at r t, okay, into 2 pi r delta z is equal to q r at r into 2 pi r delta z delta t minus q r at r plus delta r 2 pi into r plus delta r delta z delta t, okay, plus the source term, okay, plus S E into 2 pi r delta z into delta t. Okay. That is the total balance condition. To get the difference equation, I divide throughout by volume, divide throughout by delta t. Okay. You can see the factor of 2 pi will cancel out everywhere. Okay. So, my difference equation will be rho Cp into T at r t plus delta t minus T at r t divided by volume and delta t. The volume in the numerator cancels out, and I will just get a delta t in the denominator. On the right side, I am dividing by volume, dividing by delta t. Okay. So, I will get here q r at r times r, okay, that delta z and delta t will cancel out, okay, minus q r at r plus delta r times r plus delta r, okay, the whole thing divided by r delta r. Okay. Note that as far as r and delta r plus delta r are concerned, these are two different terms. Okay. The surface areas are different on the surfaces at on the inner and the outer surfaces. Okay. So, I cannot just cancel it out with this r on the left side. Okay. I cannot just cancel it out because the surface area is changing. Okay. When I find the volume, of course, I can always cancel it out. I divide throughout by volume, and I will just get S E here, where S E is the source of energy. Take limit to go from the difference equation to the differential equation, I take the limit delta r going to 0, delta t going to 0. Okay, to take the go from the difference equation to the differential equation, you take the limit delta r going to 0 and delta t going to 0, and I will get rho Cp into partial t by partial t. Okay. The term on the right is the derivative of r times qr. Okay. Value of r times qr at r minus the value of r times qr at r plus delta r divided by delta r is the derivative of r times qr by partial r. Okay. That is this term here, and I have another r in the denominator 1 over r. Okay. And this is still not quite correct, because the derivative would be the value at r plus delta r minus the value of at r. Okay. What I have on the right hand side here is the value at r minus the value at r plus delta r. Okay. What I have here is the value at r minus the value at r plus delta r. So, therefore, I should have a negative sign here, okay, plus the source of energy, okay, plus the source of energy. So, that is the balance condition, okay, that is the balance condition, okay, in a spherical, in a cylindrical coordinate system. And in order to find out an equation for the temperature field, I will have to use Fourier's law for heat conduction. The heat flux is equal to minus the conductivity times the spatial temperature gradient in the r direction. Okay, we have assumed that there is no variation in the z direction, and implicit in here is also that there is no variation around the axis. Okay. We assume that this is what is called an axisymmetric problem. This is an axisymmetric problem, that is, there is no variation in the temperature field around the axis. Okay. This is another, the third coordinate apart from r and z is actually the angle around the axis, which is often called as phi or theta. Okay. In this particular case, we have assumed that there is no variation around the axis, or that the problem is axisymmetric. Okay. And therefore, qr is equal to minus k times partial t by partial r, and the differential equation becomes rho Cp partial t by partial t is equal to minus 1 over r d by dr of r. There is no negative sign here. Plus AC. Okay, so that is the conservation equation. If rho and Cp are constants, I told you earlier that for incompressible flows rho is a constant, and in many practical situations, including for ideal gases as well as for liquids, Cp can be assumed to be very nearly a constant. Okay. In that case, I can divide both sides by rho and Cp, and I will get partial t by partial t is equal to 1 by r d by dr of r alpha partial t by partial r plus Se by rho Cp. Okay. And in the special case where there is a constant diffusivity, okay, if alpha is also a constant, then the equation reduces to partial t by partial t. You can take alpha out of the derivative. So, this is the energy balance equation in a cylindrical coordinate system. Okay, this is the energy balance equation in a cylindrical coordinate system. Recall what we had got in a Cartesian coordinate system. Okay. Recall what we had got in a Cartesian coordinate system. The equivalent equations were partial t by partial t is equal to this was what we had got in a Cartesian coordinate system. Okay. So, clearly the form of the spatial derivative in this case, okay, the form of the spatial derivative in this case is much more complicated than what we had in a Cartesian coordinate system. Instead of having just the second derivative, we have 1 over r d by dr of r times partial t by partial r. Okay. And in this case, the equivalent was rho C p into partial t by partial t is equal to minus partial q z by partial z plus A c. Okay. And the difference between these two is basically that in a Cartesian coordinate system, the surface area is a constant. Okay. So, the total heat transfer rate, since the surface area is a constant, the transfer rate is directly proportional to the flux. In a cylindrical coordinate system, the surface area is not a constant. The surface area increases as r increases, right. So, therefore, the transfer rate is not proportional to the flux. The surface area is varying as r increases, okay. And for that reason, the transport rate is not directly proportional to the flux in a cylindrical coordinate system, and as we will see later, in a curvilinear coordinate system. Okay. And it is because these two areas are different. Okay. It is because these two areas, the inner and the outer surfaces areas are different. Therefore, even though the total transfer rate is the same, if the surface area increases, the flux has to decrease, okay, okay, for the transfer rate to be the same in a cylindrical coordinate system, whereas in a Cartesian coordinate system that is not true, okay, because the transfer rate is directly proportional to the area times the flux, and the area is a constant. Okay. So, because of that, we have a slightly more complicated form of the differential operator in the equation, in the energy balance equation, in comparison to a Cartesian coordinate system, because the surface area is changing as the coordinate is changing. Okay. And so, whereas now the equation of the surface has become much simpler. Okay. The equation of the surface, the boundary, is that r is equal to capital R, whereas in this case the boundary would have been x square plus y, sorry. Okay. Okay. So, you have made the equation for the surface simpler, but however, the differential operator in this case has become slightly more complicated. Okay. So, we will examine further how this can be the equations for the concentration and velocity fields turn out to be very similar to what we have for the temperature field. They can be derived in exactly the same form, in the same manner, and then we will look at some applications for steady state transport. So, I will continue this in the next lecture. I will see you then.